Hello, everyone. Yeah, sorry we couldn't do this in person again. Had an unexpected event yesterday. I really tore my right calf. So anyway, some difficulties walking. I think there's a slight improvement between yesterday and today for those of you that have contacted me to ask. But other than going to the ER and saying that I don't have a broken bone or anything, I haven't seen a specialist. It's going to be a while before I see a specialist, but I'll do my best, like I said, to limp back into class on Wednesday. Okay, so anyway, with that being said, let's go ahead uh, and get our lesson started for today. Okay, so so we are at lecture 19 today. Okay, so we'll be recapping some of the stuff that we went over on Wednesday regarding factorial ANOVA. And then we will move on to a completely new chapter in the book. Okay, so we will start linear regression and correlation. So there's a lot of background to cover that there, just because we haven't done that before. So anyway, just a couple of important announcements in terms of the logistics for the class. We have our midterm exam, right? Exam number three coming up not this Wednesday, but a week from this Wednesday. That would be November 12th. So again, a week from today, we're looking at having a holiday. So we've got two more lectures today and Wednesday, and then next Monday's a holiday. Then we've got our exam. So again, that always comes up way faster than expected. I strongly encourage you, of course, to have a single sheet worth of formulas and strategies or notes you want to have for yourself. And yeah, that just helps you think ahead of time, like have that ready to go. As always, there's a mixture of multiple choice, matching, right? We're doing this on Canvas again, like we've done for exam one and exam two for this course. And calculators are studio's fair game, right? But no other electronic sources may be used for the exam, as we've done before already. So an important thing to point out now is that the topics that we'll cover in exam three are the following: confidence interval hypothesis testing for single mean, for paired data, for unpaired data, and then one and two factor ANOVA, part of which we're kind of wrapping up now in the next 15 minutes. So again, linear regression, the new chapter that will start today after wrapping up two factor ANOVA, will not be part of your exam three. That's going to be part of the final exam. Okay, so just making that clear now. Um, what else is fair game? Content of lab six, seven, and eight will be fair game. Again, you did lab seven was turned in over the weekend, and that was regular ANOVA. This week's lab eight, will be factorial ANOVA. So that said, there's some problems that associated with that too. Again, I just want to reiterate that linear regression will not be covered in exam three. We're going to save that for the final. Okay, reading for today, chapter 8.1 through 8.2, reading for Wednesday. Um, okay, that should be a corrected date there. I'll make sure to correct that before I send this PDF. Should be chapters 8.2 to 8.3. Suggested practice exercises are there. And as always, we will have a lab due on Friday and a problem set due on Thursday. Okay. The lab is due on Friday by 1 p.m. We just like to get as many of those graded as possible before leaving for a weekend. And then the problem set is due at 11:59, right? Like the 11th hour of Thursday. Okay, the night before. Okay, the goals for today are the following. We're going to start by recapping this two-factor ANOVA business and basically continue to talk about interaction plots, which is where we left off on Wednesday. Then we will move on to introducing linear regression. We'll talk about what a linear model is, what are the terms that go into a linear model, what are the linear models hoping to accomplish, and then we'll talk about errors associated with observations relative to the model or something called residuals, and then talk about something called correlation. Okay, so yeah, let's go ahead and get that started now. So we've been playing around with ANOVA for over a week now. And again, regular ANOVA, right, is an extension, not a direct extension, obviously. It's a completely separate test, but it's an extension of what we initially set out to do with the t-test, right, when testing for true differences between two means. The regular t-test, right, has an expected amount of error associated with it. And that error, we agreed, exponentially grows. with the more groups that are compared, right? So I think that our t-test approach is perfectly fine for comparing two groups, right, at a certain critical value. But if you were to compare more groups, the probability of finding false positives increases really, really fast. You're basically guaranteed to generate a false positive if you've got five groups that you're comparing. So anyway, to that extent, right, we talked about another approach to analyze variance or the sources of variation, right, being partitioned for noise between the groups versus noise within the groups, right? And coming up with a new statistic called the F statistic, so on and so forth. And we've done a lot of that, right? So anyway, moving on from that regular ANOVA, right? We moved on to this idea of factorial ANOVA or two-way ANOVA, where you have numerical continuous data that belongs to different levels of at least two factors. Okay, so two factors could have different levels, right? Even different number of levels within each one of the factors. And basically, all of your numerical continuous data can be grouped into cross-sectional groups of the levels of these two factors, right? When you have a setup like that, you're talking about this factorial ANOVA business. And again, there's three hypotheses that factorial ANOVA is really going after, right? The first hypothesis is that all the groups, according to the first factor, have the same mean. So this is called the main effect. And again, this is more or less equivalent to ignoring the fact that factor B exists and then seeing and then grouping data based on the levels of factor A and doing an ANOVA for that, just a regular ANOVA for all intents and purposes. The second hypothesis of a factorial ANOVA is doing the same thing for the second factor or factor B, right? Ignoring the factor A exists, and then seeing if there's true differences between the different levels of the second factor, factor B, right? And again, that's pretty easy to contextualize, right? Pretty straightforward stuff. We've seen that before because we did ANOVA for a lecture and a half before coming up to this factorial ANOVA business, right? The third hypothesis there is a little more interesting, right? So this third hypothesis is one that we had never seen before this factorial ANOVA stuff. And this third hypothesis involved the interaction between factors and how um, your numerical continuous response variable may be affected differently as a function of which level of the different factors it happens to be grouped under. Okay, so that's a third hypothesis again that factorial ANOVA will allow you to explore. All right, this is called an interaction. If there's differences in the mean of the numerical response variable as a function of different combinations of levels across a factor, then that is considered an interaction. Okay, that's where we left off talking, right? Last time on Wednesday or last week on Wednesday. These interactions are super cool things to like interpret and for whatever a number of different experiments and situations in biology do involve interaction. So I really enjoyed thinking about them. And we even talked about something called an interaction plot, right? Which is basically plotting the means of one of the factors across X values that represent levels of the other factors and seeing where those interactions are happening or what the nature of those interactions are, right? So that's what this interaction plots are supposed to do. So again, to summarize that really quickly, right? Like what are they useful for again? Well, this two-factor ANOVA interaction plot will ultimately visualize how two independent variables or factors jointly influence a dependent variable specifically. All right. And this is to detect whether the effect of one factor depends on the level of the other factor. All right. So again, at the end of the day, the interaction plots are not a diagnostic. They are not a test, right? You actually have to run the two-factor ANOVA, all right, computationally or by hand. I guess in this class, we only do it computationally. And then you have to look at the p-value, right, in order to test that against a critical value or an alpha and see if the null hypothesis, right, for each one of these three hypotheses, meaning that all groups have the same mean, is that statement which is null, right, null hypothesis. Is there evidence against that statement or not, right? Is there evidence against the second statement? And also, again, even though you may have like this nice interaction plan, understand what, and you think you understand what's going on there, you still have to look at the p-value for this third hypothesis and then let that p-value tell you whether or not there's an interaction expected between the factors. Okay, so cool. With that being said, let's go ahead and yeah, let's revisit this for just a couple minutes here. So again, I won't go over this in too much detail, right? We talked about this data set quite extensively on Wednesday. So here we've got your classical two-way ANOVA setup, right? We've got numerical continuous data that belongs to one of two factors, right? The factors here of this data are either type of flower media that's basically used to grow pupa of these insects. Okay, the response variable here again is the weight of the pupa in milligrams. Okay, and again, any one of those responses can be grouped into the type of flour media that was used to feed the pupa. And again, that would be wheat, corn, or oat. So there's three levels to that first factor of media type. Okay. We have this other factor here, right, of like whether the pupa was sex as a male or a female. All right. So we have a second factor there. And again, any one of these observations, right, numerical continuous observations, can also be grouped into one of the two levels of the second group, right? Female or male, level one or level two of the second group, which is sex of the animal. Okay, so anyway, this basically creates intersectional groupings, right? That oh, this is what I was talking about. Yeah, you end up with this intersectional groupings for which you can derive a mean, right? An average, specifically a mean, and then try to see how these means change as a function of levels of the two different factors. So again, here we have a total of six groups, right? Mel and wheat flour is the intersectional grouping that I'm highlighting here specifically. Right? So again, the intersection of two factors. What we would want to do overall with the two factorial ANOVA, again, is harkening back to our three hypotheses, is ask whether or not there are differences between the diets. Right? So what does that mean? That first hypothesis there pretty much means ignoring um, the second factor, right? Like independently of whether the data comes from a female or a male, you can just randomize this column, right? And come up with the same mean for the weight of the pupa that's been feeding on wheat, right? Versus the weight of all the pupa that have been feeding on corn and the weight of all the pupa have been feeding on oats. So essentially, this first hypothesis is more or less a regular ANOVA, like we were seeing before doing factorial ANOVA. Okay. Um, Similarly, we can do the same thing for the second factor, right? Like not caring about what the value of the first factor is, right? We can just randomize all of these observations in the top half there across the three columns and just call it female, and randomize all of the bottom observations right here and call those male observations, and then see if there's differences in those means. And again, essentially, that's a second ANOVA that we're running here. Again, the third most interesting hypothesis that you can get out of this factorial ANOVA is whether or not flower type, right, may affect female beetles differently than male beetles, right? And like there we're talking about an interaction term. So the null hypothesis is that there should not be an interaction. All right. And like I have a handout on Canvas that goes really deeply into that. All right. We won't cover it too much now, but I mean, there's a formal way to say that, right? Like whether or not the factors are additive would mean, if the factors are additive, would mean that there's no interaction. If they're not additive, that means that you would expect an interaction. Okay. Again, you may not always see the interaction. We do an interaction plot, but you got to go by the result of the test, not by your own interpretation of the plot. Okay, talk about that more in a second. But again, just to reiterate this, this is a completely new question type that we've never explored in this class before. Anyway, again, all of this data, for example, just goes into R. This is what we'll be doing this week, two-factor ANOVA on R for your laboratory assignment. And R will give you this output, okay? And in this output, you basically have three F statistics, all right? Those F statistics, again, are how we generate a p-value, right? So there's a probability mass function curve, right? That's a function of the number of groups and the number of observations, right? R is doing all of this for you in the background, of course, picking the right curve. Once you have the right curve, or once R has the right curve, it then generates an F statistic and then sets that F statistic on the curve to then figure out the area under the curve that's more extreme than your F statistic And that's how you get that p-value, the final column there. The sources of variation basically refer to the three hypotheses that the factorial ANOVA is targeting, whether or not there's differences across the levels of diet. Okay, that is that first hypothesis in the first row that you see here. Those are all of the statistics for testing that hypothesis, all right? And then eventually a p-value. Clearly, at an alpha of 0.05, this p-value would indicate that there are significant differences, right, between the diet types, right, ignoring sex. Significant differences there. So again, pretty high F statistics, so a tiny area that's more extreme than that F statistic. So we can basically say that there's enough evidence to refute the null hypothesis. There are differences across the sexes, or sorry, the diets. Jumping ahead here, going to the second line, you can explore whether or not there are differences between the, okay, this might be my physician. One second. Okay. All right. Mic check. Mic check. Yeah, I don't know how much you guys heard about that, but it was just me scheduling my specialist appointment. Okay. All right. Coming back to this again. Sorry, reframing here. So again, the first row there is the results of of the first hypothesis, right? Asking whether or not there's a difference between the means for the different levels of diet, right? Again, that's your F statistic in the penultimate column there, first row, and then your p-value associated with that F statistic. Again, F statistic would be a place underneath the mass probability function um, that represents the area under the curve that is associated with a more extreme observation, right? So pretty small p-value. That's a lot of evidence to refute a null hypothesis at an alpha of 0.05, right? So there are differences between the different levels of diet, corn starch or whatever it was, differences there. Okay, next row shows us the same summary for basically an ANOVA for testing the potential for differences between the levels of sex, right? The levels of sex are just two, male and female, right? Biological sex for these beetles. And what we see is another extremely high F statistic that's, of course, accordingly associated with an extremely small p-value. All right, that p-value is also lower than 0.05. All right, this third role now is addressing our third hypothesis for the factorial ANOVA. And that third hypothesis is whether or not we would expect an interaction. All right, there. And the null is that there's no interaction. And what we see here is, again, an F statistic of 4.38, giving us a p-value of 0.03. All right. That p-value is technically significant evidence against a null if our alpha remains at 0.05. All right, so we would expect some sort of interaction there. Okay, so that's where we're at with this ANOVA table. So again, nothing new here, just different rows in terms of how to interpret the factorial ANOVA compared to a regular ANOVA that we've done before computationally too. Okay. Okay, let's go ahead and move on. Okay, so we're back to our interaction plots, and I think this is where we left off on Wednesday, right? Here we are plotting not individual observations, right? We're plotting means of one factor level against another. All right. In this particular setup, the x-axis shows different levels of diet as a factor. All right. So we're talking about different levels of different types of flour that represent the levels of diet, corn, oat, and wheat. All right. The y-axis is our numerical response variable. And then for each one of those levels, we plot the average of the average for each one of the other factors levels. Okay, and that's what we're seeing there. So again, I guess those are error bars, or I guess distribution. Just keep in mind that each one of these dots represent the average, right? The mean specifically of a cloud of dots that are that same color, right? Because it's different observations, right? That you generate a mean for right there. So anyway, what we see down here is that there is basically an equal mean for females and males in terms of the pupa weight, right? When both fed on corn. All right. As we move across, right, the level corn to level oat for diet, we see that the weight for males and female changes. All right. The average weight for the pupa changes, but it's changing in opposite directions, right? We see that the average weight for the males decreases. Males are in pink here, and then we see that the average weight for the females increases. So this is evidence for an interaction effect, actually, because that means that the level that you're in terms of diet disproportionately affects the outcome for the level that you're in terms of sex. All right, there's a differential um, result when going from a corn diet to an oat diet, right? The males grow lighter, or they're smaller, and the females grow bigger. All right. So that there's there you go. So that's kind of visualizing what the p-value, right? Like already had suggested for the third hypothesis. All right. All right. So what else do we have here? We have then the next level over, right? Because we got a total of three levels for diet. When we look at oat relative to wheat, right, we see a net trend for both males and females of gaining more weight on average, all right, for these pupa. So again, here you see an effect of the level, right, oat and wheat, but that effect, yeah, the effect that you see here is strictly derived from changing diet, right? But it's and that change in diet is equally affecting or equally or effectuating the same outcome in both males and females. And that same outcome means that they both weigh more, basically. Okay. So that's where we're at. And I think that's where we left that last time. So again, this is pretty useful to uh see what's going on there, right? Like again, and depending on what question you're asking for the specific experiment that you're investigating interactions for, this step might be a lot more interesting than the other step. Okay, but again, your job for the exam is just to identify based on the interaction plot whether or not there is an interaction or if there's an effect across levels, right, for one factor or the other factor. So that's kind of what we're playing around with here. Okay, factor B. Okay, so here, but I guess I'll just go to like one or two other examples before moving on to linear regression. What are the factors here? How many factors, how many levels per factor? So pretty straightforward questions that you'll see me asking in the exam, right? So the factors here would obviously be dose and treatment, okay? Dose, I guess, has two levels, right? It can either be high or low dose for whatever medication we're talking about here. And then treatment has three levels, right? The treatments are can be, I don't know, like taking the medicine once a day, twice a day, and I guess not taking it all. I don't know if I just kind of made this up as I went. Again, the main effects would be whether or not there are differences for the levels of one factor at a time. Okay, those are the main effects. So let's look at that now. Let's look at treatment. All right. Um, yeah, one factor at a time. So if we look at treatment only, right? A, B, and C, um, we would ignore that those even exist. Okay. And again, this might be triplicates that are summarized with that mean. This might be triplicate pairs that are summarized with that other mean and low, triplicates here, triplicates there. Long story short, I think that if we were to visualize all of the observations that came up with this means, right? The mean for all of the data independently of the dose, right, would be right there in between those two. All right. The mean would move slightly higher here because I think that there's a positive trend there, but I don't know how much higher, honestly. I think again, and I'm just looking at the mean for treatment, right? That would be all the data for treatment A, independently of dosage, would have a mean that's right there in the middle, another mean that's pretty close to the middle, if you ask me. And then again, even though there's a severe difference here now, if you consider the dosage, right? If you ignore that, it would just be a cloud of dots here that with that mean, and a cloud of dots down here with that other mean. But again, if you're ignoring the color, the mean of all of those data points would probably be right here in the middle too. So I don't know. I don't know if there would be a main effect for treatment, right? Like I'm not sure if there would be statistically significant differences in the means for each treatment level if we were ignoring dose. Okay, so that's what I'm talking about there. So that's how you would go after a main effect, one factor at a time. All right, in terms of interaction here, I think that it's pretty clear, right? We see that going from treatment B to treatment C, right? So a different level for one factor, right? Treatment B is level B for factor treatment. Treatment C is level C for factor treatment, right? Switching between those two levels of that factor, right, gives us differential outcomes of the other factor, right? The other factor is high dose and low dose, right? Again, moving over from B to C on treatment gives us lower values for the low dose and higher values for the high dose. So I think again, the fact that differentially they're uh, differential outcomes, right, across the levels of or differential outcomes emerging by switching levels of one factor means that there's an interaction basically. So that's how I would interpret that one. Anyway, okay, so again, a couple of fun cartoons here, right? Here again, this would be whatever trait measure, weight of lizards, weight of Komodo dragons, I guess, across like one island and another island in the archipelago, right? There, like Island One and Island Two would not have an impact at all, right? On the mean weight of all these dragons, right? Completely making this up as I go, right? And then let's say that you had males and females, males in red, females in blue, that wouldn't have uh that doesn't make a change here either, right? For if we interpreted that or if we were going after this outcome. Okay, so no significant effects at all. The mean for both of the levels of the first category in red and blue stay the same. And for both of the levels of the second factor, right, environment stay the same. So there's no effects at all, no significant effects. That's how we would interpret that. Okay, looking at the second plot here, in panel B, we see that across both environments, there are differences in the means of the males and the female Komodo dragons, or whatever you want this to be. Um, and those differences, right, would indicate a species effect, right? Because again, independently of which level of the factor of environment, basically, independently of which island you're on, um, the the males are heavier than the females, basically. So there's a species-driven effect. However, though, if you were to ignore which data points that you use to come up with this means are male and which ones are female, they all turn black, basically. There's no red and blue. The mean for all of these would be right there in the middle. I'm not sure if you guys can even see that, so let me get my laser pointer. Yeah, the mean for both of these would be right here in the middle, and then the mean for both of these would be right here in the middle. So the actual mean, right, uh, for all data point across environments, independently of, I guess, a species here, not sex, so independently of species, would make no difference. All right, so there wouldn't be an environmental effect. Conversely, here we have more or less the same mean for, I guess we're talking about two species now. Red and blue are different species. We have the same mean for both of those colors, right? In environment one, and the same mean for both of those colors in environment two. All right. But those means are different from each other across the two environments. So that would be an environmental effect. Okay. Here we've got an interaction effect now. So the mean across environments is not changing. I hope you guys can see that now. Again, this red dot represents a mean of a bunch of other red dots around it. This blue dot represents a mean of a bunch of other blue dots around it. The same thing here and the same thing here. If both of these, or if we were ignoring the color of the dots and just looking at the means of what would be all the combined dots here and all the combined dots there, the means would probably stay the same. I'll say the mean independently of the color of the dot, right? For all of the data point in environment one would be right around there, and then the other one would be there. Okay, everybody see that? So there wouldn't be an effect on the means across the environment, but going from one environment to the other environment changes differentially changes what you get as a function of one level of the other factor or the other level of the other factor. So again, going from one environment to the other in this case would make the red species lighter and the blue species heavier. All right, if we were measuring weight or whatever. So that's again, the ANOVA test will just tell you that there is an interaction. All right. It will tell you what the main effects look like. All right. But it will not help you interpret those statistically significant results, right, into a story for the question that you're asking experimentally. So that's when these things come into play. Okay. So hopefully that's relatively straightforward. Just super briefly here, a couple more scenarios. Here we would have an interaction and species effect. So across yeah, again, note that the mean for all of these data across environment one, environment two is the same, right? There's a lot of observations up here now, a lot of observations down here, but the mean is right there, okay? And the mean is right there for environment one. Again, mean right there for environment two, mean right there for environment one. All right. However, there is a species effect, right? So it looks like the red species is always heavier or whatever this y-axis is. Let's just pretend this weight. It's always heavier than the blue species. All right. So that would be a species effect, right? The difference is really exaggerated in the second environment. And also, there appears to be different directionality, right? Going from this environment where both of the levels, right, of species, right, weigh the same to the second environment where they don't weigh the same, right? One species is weighing less than the other would be indicative of an interaction. Okay. What do we have here? Let me move my screen out of the way. Here we would also have an interaction and an environmental effect in this case, right? So again, the mean here for this environment is there. The mean for the second environment is up here now. So the mean is changing across the levels of environment. Okay. Um, Yeah, and I guess that the difference in the means between the levels of species, right, blue versus red, is more or less the same, but it's inverted across environments. That inversion indicates an interaction. All right, so I talked about that in class. So every time you see lines that cross each other, it's more than likely an interact. It's more than likely always an interaction. Interaction, same species, environmental effects, so on and so forth. So I have more examples here that I think are pretty useful cartoons. All right, that I'll let you guys play with on your own. All right, and again, like if these are relatively straightforward to get, but if you are struggling with that, make sure you come see me during office hours and we'll walk through them together. All right. Obviously, this is my chicken scratch handwritten notes, but there could be multiple levels, right? For one factor and only two levels for the other. So understanding how to see if there is an interaction or which levels of which factors are effectuating the interaction is, again, should be extended for more than two factors with two levels, right? You can have more than two levels per factor. Same thing here, um, so on and so forth. So anyway, I think at this point, I think I'm comfortable moving on to linear regression. Okay, so let's get the ball rolling with that. So we're pivoting themes here, leaving behind ANOVA, and moving on to linear regression and correlation over the next 30 to 40 minutes. Again, I want to reiterate that starting now, this material will not be covered in exam three. Okay, just keep that in mind. Okay, so linear regression. Okay, so we've all done plotting of a line before, right? So I think that this is a pretty basic concept introduced in like middle school usually. And yeah, and this is the basic way to write down the equation of a line, right? So yeah, you have the rise over the run, right? So that's called the slope. That's what you get here. And then you have something called a y-intercept, right? And that's this y-intercept and the slope give you the equation for a line, right? So you can find out what any y on this line is if you know an x, right? You just plug in x and you get what y will be. And that's how the equation of the line works, right? So again, super useful um, mathematics here. Pretty simple mathematics, but that are actually quite powerful, right? A lot of important concepts in science are based on linear regressions. So super important stuff. But again, slope is rise over run. And that's what you get here. And then y-intercept would be this. All right. And if you want to know any y, right, any level of y here, you can do that by just plugging in an x and solving for the equation. Okay, so again, pretty useful stuff. The x-axis here we would call the predictor variable. Okay, the y-axis would be the response variable. So again, you can make a prediction for what y is for any given x. And that's what linear regression is basically uh, based on. Okay, so again, we've got our model parameters here. So again, um, real data is never this clean, right? So what I'm showing here is like a perfect depiction of a what would be an incredible linear regression, right? It's never like that. A single line can never truly encapsulate natural observations or observations about nature. All right. The line can approximate more or less the trend that the observations follow, but the observations are always a little bit above or a little bit below a, a regular mathematical object like a line. Okay. That so again, what we the line ultimately aims to do is to capture the trend of the observations, but it never really looks like what I'm showing here. This is way too linear. But anyway, the line itself is therefore not reality, right? The line itself becomes a model of the trend that we're seeing experimentally. All right, so this is why this is called linear modeling. So again, fitting observations or fitting trends of observations to lines, all right? And lines can be polynomial too. So we can talk about hyperbolas, we can talk about exponential growth, we can talk about logarithmic lines, right? In this case, we're just talking about super simple classic line with the slope and intercept equation, okay? Um, and anyway, that line, right, like that equation, that mathematical equation becomes our model, right, or becomes our best possible estimate to with a single predictor variable, whatever x is here, come up with a value that we would expect to see in nature, whatever y is. Okay. And okay, so this line again, or this model becomes this, or the equation of the line becomes our functional model. And that's what I'm showing here. All right. So beta naught is the y-intercept of this linear model. Beta 1 is the slope. All right. And those two things are key to having a mathematical object, again, just a line in this case, capture the observations and trends. Okay. So that's what we call the linear model. All right. Those are called parameters of the model. Okay. Parameters of the model are the uh, ineluctable things that you need to inform a potential prediction. Okay. And this second parameter, the slope, right, is what you multiplied against your predictor x in order to come up with a given y. In formal modeling, we do formal modeling, a lot of linear modeling in my advanced biostats class. Okay, you have to consider this other term too, called the error term. But for all intents and purposes, in this class, we will just focus on the first two model parameters that I'm showing here, the slope and the y-intercept. Okay, so again, oh, jumping ahead. All right, once again, I had this slide that I was just talking about. So real world data are never perfectly linear. Okay, so let's just get that out of the way now. Um, you will never see relationships, okay, that are perfectly linear. All right, there's always noise because of the way things are measured, or the way things are measured, mismeasured is a potential source of variation or noise, okay? But that's interesting noise, but not the noise that we're going after with the model. Usually we want the model uh, to explain the nature of the world. And the nature of the world should not be us making experimental errors, right? So the sources of error in that model are key to coming up with strong predictions. But anyway, I'm jumping ahead. Let's just say the following, okay? So again, like I said, real world data are never perfectly linear, but sometimes a linear relationship is not a bad approximation of what's happening in the real world. All right. So with that being said, this is what I'm talking about here. So let's look at this more real world data here. So we have a scatter plot below that's kind of a cartoon, but it's supposed to represent, geez, one second. Okay, so I have kind of more or less a cartoon here, but it's supposed to represent height as the predictor variable and foot length in the y-axis as the response variable, okay, for college students. So this is pretty interesting, right? I'm not sure if I broke this down to female and male college students. I don't know, but the bottom line is the following, right? Uh, there's a couple of observations here, right, that allow you to develop a trend. All right. So these are probably people that you were able to measure both their height and their foot length from. Each one of these dots represents a person or a database, right? That's then used to draw a line through the data, right? And then the line becomes the model for future predictions. Okay, so that's what we're talking about here. So again, there's all of these observations that we have, right? And it's never perfect. There's even a crazy outlier here. I guess this is someone that's incredibly tall that has relatively small feet. All right. So I guess people like that exist, right? So there it is. You have that outlier, right? But essentially, what you're trying to do with this line is capture the nature of the trend, right? And again, none of those observations are actually part of your model. Maybe this one, that's a pretty close observation, but again, this is continuous data, so it'll be off at a particular decimal point too, you know. So none of these observations are actually on the line that you're calling the model, but that model, right, can be saved as a mathematical equation that will allow you to make predictions, right? So again, for example, you've got no one in your database here that is 80 inches tall. Exactly. You have no one there that's 80 inches tall. But if you could use the equation of that line and then plug in 80 as your x into the equation of the line to then make a prediction to what foot length that 80-inch tall person would have in centimeters. Okay, so that's the strength of capturing a trend, right? A database trend in a mathematical equation or linear modeling specifically. So that's what we're looking at doing here. So again, none of these models are perfect. Okay, there's always error with any model you can think of. But yeah, just keep in mind that with very simple parameters, right? In this case, just a y-intercept and a slope, right? We can have a very functional tool to make predictions about many phenomena in nature, right? So yeah, I guess uh my favorite linear relationship is probably Hubble's law, right? So I don't know if you guys are familiar with that, but yeah. So Edwin Hubble, right? That Hubble Space Telescope is named after, and actually our local soccer team, the Galaxy, right? It's named after him studying galaxies, basically. While working right above Pasadena, in the Mount Wilson Observatory, became interested in like stellar nebulae. That's what they used to call galaxies before they knew that they were basically island universes, right? Like entire galaxies. And yeah, he plotted distance of that galaxy against speed and then came up with Hubble's law, which is again just this crazy relationship of how galaxies that are further away from us seem to be moving away faster. And that's basically the start of the Big Bang Theory, right? Again, right like 6 miles north of our campus, like the Big Bang was born, basically. And I mean, he didn't set out to say the universe exploded, and it's expanding. That's just what the data told him based on this very simple linear regression that, he used the equation of a simple line to um, uh, to uh, to come up with. So I think that's remarkable. And again, I'm just highlighting the strength of like something as simple as a line, when interpreted properly. Or to model a phenomenon, in nature. So again, not really biology here, but it's my favorite example of like a simple relationship that means a lot. So anyway, moving on. Okay, yeah. So this we got a couple of goals here. Okay, so again, I'm talking about the model parameters a little more here. So we've got our beta naught, which is estimated from the data. Okay, we've got our beta 1, which is also estimated from the data. And like I mentioned before, you're going to want to ignore that error term for now. It's a formal parameter of a model 2, but that we just don't get to cover in this class. All right, so that is those are our model parameters. As always, the Greek letters, right? Like actual beta, naught, and beta 1. Are the ideal parameters that we'll never really get to play with, right? All we have is lowercase b naught and lowercase b1x. And those are our actual estimated, uh, those are our actual estimates of beta naught and beta 1 from the data that we have available. Okay, and those estimates can change, obviously. They change a lot if you do something called Bayesian stats, but they change a lot, or they basically they can change if you have additional data points or if you happen to take out some data points, they get changed. But again, those are estimates of the true model parameters. Okay, so that's where we're at with that. The goals here, basically, with linear regression is to understanding the criteria for fitting a line in the first place, right? Which line out of many lines that can be fit across across a particular data set that has a linear trend, which one's the best one and why? We want to understand the uncertainty and parameter estimates, right? So again, we're estimating the parameters, right? Beta naught and beta 1 right here with the Greek beta are the true parameters of this model. Okay. However, we don't have access to those true parameters because we don't have all of the data in the population, right, that we're trying to model a relationship for. So what we have is a limited number of observations, and therefore what we're going to be working with are estimates of these two parameters. Our estimates based on our limited number of observations are little b naught and little b1x. Okay, so again, little b naught would be the estimate of beta naught. Little b1x would be the estimate of our other parameter here. Okay, which is basically the slope of the equation. Okay, so we want to identify if fitting a line to a relationship is even useful before getting too far ahead with this linear regression stuff. So let's move on to that. Okay, right. So what we have here is again a bunch of observations, all right, of these bush-tailed possums. I mean, they look super cool. So I guess all possums are marsupials. You guys know that's a really weird thing that I didn't know until not too long ago. Opossums that we have here in Southern California are like the only American marsupials. So even though I guess people often misconstrue them as giant rats, I guess you and me are more closely related to a rat than a marsupial could ever be. Yeah. So yeah, we probably shared a closer common ancestor with rats. Marsupials share an ancestor with a rat. So anyway, long story short, this is an actual marsupial from Australia, right? And there's a ton of these marsupials um, that have had their total length, so I guess that's from snout to tail, um, measured, okay, in centimeters. So pretty big animals. And also their head has been measured independently. So just the whole body measurement and then a head measurement. And the head length is here in millimeters, obviously a smaller head than a body, so you go from centimeters to millimeters. But either way, we have this data distribution here now. Okay, so the relationship between total length and head is estimated by the following. Okay, you can draw a line through this data, right? And basically make yourself believe, right, that this data is following a linear trend, right? The line captures a ton of the variation of this relationship between total length of the body and head length for these bush-tail marsupials here. Okay, so just have a look at that. But again, remember that line is a summary, a very imperfect summary, because no one actual observation is actually on it, right? It's just summarizing the trend for all of the observations collectively. All right. That trend can be summarized mathematically, and this is the equation for that line. Again, 41 would be the y-intercept, 0.59 would be the slope, the rise over the run. Okay, so for every one movement in the x direction from 80 to 81, how many units of y do you move up? 0.59. So that's what that represents again, rise over run or slope. Thus, for a possum of a total length of 80 centimeters, all right, we're able to now make a prediction. Okay. Again, I don't understand why we couldn't measure the head ourselves, but if we just had data for the length of a possum, right? Oh, okay, that's where this could be useful. Let me explain how this could be useful. Um, this data set here is probably something that we went out to get now. Okay. Maybe historically there's records the possum, bush-tail possum populations that didn't specifically measure head size, okay, but did measure full animal size. I don't know, maybe 50 or 100 years ago. Okay, for whatever reason, they didn't measure the head size. But if we go back to that data now, given that we've got a linear model of the relationship between total body length and head now for the same species, we go back to data from the same species from 50 or 100 years ago, we would be able to come up with a prediction for what the head length should be, given the body length only. That's what we're looking at now. So again, for a possum of total body length of 80 centimeters, right? We're looking at being right here. We can just simply plug in 80 here into X, right? That is our predictor, 80. X gets replaced by 80. You multiply that by 0.59 and then you add 41 and you get your Y prediction, which would be the value that's equivalent here on the Y axis, right? And that Y prediction would be 88.2 for as millimeters now, okay, for the head length of that animal. So again, we consider an 88.2 an average reasonable estimate of head length based on total body length, all right? So again, we're modeling the head length using linear regression. Note the variation around the estimate, all right? What else may contribute to bush-tailed possum head length that is not considered in our model? All right, so obviously, there's a ton of other things other than just the length of the body that could be contributing to the length of the head of any particular animal, right? I mean, just from an evolutionary perspective, there might be subpopulations, right? From a nutritional perspective, there might be slight micro cephalic, like smaller face possums, based on which part of Australia they live in, right? Maybe there's just like crappy nutrition in one part of the countryside versus better nutrition in another, right? So there's many different considerations that could be essentially confounding variables influencing uh, influencing how tight the relationship between total length and head length is. All right, so there's a bunch of things that we're not assessing right now. We will totally come back to this idea when we do multiple linear regression, right? So again, kind of jumping ahead a little bit just for a second here, you can also have um, many predictors generate an estimate for head length, for example. If Y is still head length, here you can have many predictors. Right now, we're just playing with body length, which is depicted here in red, but we could also add um, additional parameters that are predictive parameters like sex, right? That's a huge one, right? Maybe there's a different relationship between male and female bushtail possums total length and head length, right? So that would be interesting to put on there. And also location, like I was mentioning, right? Like some sort of nutritional deficiency in like iron or some sort of mineral, right? That can affect the ultimately affect the length of the head independently of the length of the rest of the body. So yeah, those are potential confounding variables that you could easily incorporate into a multiple linear regression model. Again, we don't play around with these for another or we'll see this at the end of the week, I think. Yeah. So anyway, okay. So that's other things to keep in mind, right? Just stay tuned for that. But for now, we're just back to considering a single predictor. Okay. So what do we want to do here? We want to understand linear model trends and uncertainty. So yeah, you can draw a line through almost anything, right? But lines are most useful, right? When the trend is pretty clear. All right. So, what do I mean by that? There's a way to quantify how well a line fits data. All right. We'll get to that in just a second. But just very briefly, right? Looking at these, obviously you can have linear um, trends that are negative, right? That as you increase the value of your predictor variable, the value of the response variable decreases. That would be the example that I'm showing here. Here we've got a positive trend, right? As we go up in the value of the predictor variable, the value of the response variable increases would be a positive linear correlation here, a negative linear correlation there. The negative linear correlation here looks a lot more tight, right? Meaning that this line is actually closest or very close or relatively more close to a lot of the observations that we see there, meaning that this is probably a stronger model than this one, right? This positively correlated line is a little more loose, right? There's a lot of variation between a lot of the observations and then the mathematical object or the line that we're saying can encapsulate the relationship. Okay, this would be extremely loose, right? And actually, when you lose a slope, you lose any predictive power. All right. So any line where the slope is just really, really flat, almost flat across, right? It's probably not a very good data set to it's not going to be well encapsulated by a linear relationship of any kind, actually, right? If you have a flat line, that means that you are predicting the same y for any value of x that you can throw at this. So there's no prediction possible if you've got a flat line. There has to be a slope, right? There has to be a change across x that leads to a different value of y for any model predictions to be made. All right, so if we got flat lines like this, with especially that happens with this much error, right? It's impossible to know which way that line should go. Then you've got a very low predictive capacity. Okay. Yeah, so flat lines are just bad, right? So I guess this would be a pretty well fitted straight line to the data that's here. But obviously that if we're using this flat black line, right, to predict the values of this relationship, even though it looks perfectly fitted because it's the same number of same amount of error basically above and below the line, it would not be a very good linear model, right, to be used with the equation for a simple line, right? That's more or less a polynomial line. So again, a clear relationship here, right? There's a relationship that it's actually well encapsulated by this super flat line if you look at this parabolic data set. But it doesn't mean that a straight linear regression would be a good fit for a model. Okay. So hopefully that makes a little sense at least. Let's have a look at what we have here. So again, for each one of these six plots, we want to identify the strength of the relationship, weak, moderate, or strong in the data, and whether fitting a linear model would be reasonable. So again, here we're stuck with another parabola. So yeah, the relationship there will probably be flat. I don't know if this would be probably not a good linear model data set. this would conversely, right? This would be a pretty good data set for a linear model, right? You can very easily think about drawing a line through the middle there, and that line being actually relatively representative of the net trend that all this data are following, right? So that's probably a good one. Here we're looking at another bad one, right? I have no idea, even if I squint really hard, which way I could draw a line that represents the trend of whatever's happening here. There's basically no trend, right? I think that the line that would be closest to all of these dots is basically a flat line again. And if you have a flat line, you don't have a slope, you don't have any predictive capacity. So again, that's a bad one. All right, so here we have another parabolic shape, right? This is another good linear one, just a negative trend in this case, and then a flat one here again. So yeah, so that's the summary, I guess. Strong linear is E. Yeah, this is probably the strongest one, right? And by strong, we mean that there's a really tight coupling of the number of dots that are going to be above that line and the number of dots that are going to be below that line, and all of those deviations actually being pretty close to what would be our mathematical object or our equation of a line, right? That we would then use to make predictions. Okay, so this residuals are super important. So let's just talk about these now. So the residual, okay, is more or less the model error. All right. And the, I guess the official definition, according to the book, is that it's the difference between the observed and the expected value of the linear model. Okay. So the residual observation for the ith, that means any given observation, right? Um, uh, in um, um, in X and Y is the difference of the observed response, yi, and the response that we would predict based on the model fitting, y hat I. Okay, so again, what does that mean? Let's calculate a quick residual here. And all right, before we even calculate it, keep this in mind. A major goal of knowing that you've got the best possible line that the most accurately encapsulates the relationship here. A major goal of that is to have the lowest amount of error, right? And if this residual is your error, you want to make sure that your line minimizes the magnitude of residuals for all of the possible observations. So that's what we're going at with this model fitting routine. All right. Again, model fitting routine just means tweaking your slope so that that slope is as close as possible to all of the observations. That literally means that's that line having the smallest magnitude of residuals. All right, so yeah, the major goal here is to in line fitting is to have the smallest possible residual distances. All right, so let's look at how to technically calculate a residual. It's pretty straightforward stuff. So let's go ahead and say that our observation is 77.0 and 85.3 for whatever it is that we're measuring here. I think we're back to the bush-tailed possum. Okay, so X for our observation again is 77.0. So we have an animal that's 77.0 centimeters in length. All right, somewhere here. All right, and we actually have this animal. All right, and we measure the body length and then we measure the head. And the measurement of the head is 85.3 centimeters. We have the animal, it's right in front of us. We got the data. The head is measured at 85.3 centimeters. That's what that X shows right there. This is the animal, the exact animal that we're talking about right now. All right. So we had this model, right, that existed with like previous observations of other animals, right? The model is the black line that you're seeing here. All right. And this is the equation for that model. We looked at this equation 3 slides ago. Y is equal to 41 plus the slope, which is 0.59 times x. All right. So let's pretend that we didn't have a measurement, a direct measurement of the head of the animal. Okay. Let's pretend that we just have the length of the animal, 77 centimeters, right? If we plug that into this model, okay, we would get the following. Plugging it into the model, we would get 77 times 59 plus 41. And the model predicted head length, this y hat of x. Y hat is a model prediction always, okay, of x, would be 86.4 millimeters for the head length of this animal of a body length 77 centimeters. All right. So how off are we is the residual, right? This is the full observation, again, knowing that we picked up an animal that was 77 centimeters long and had a head of 85.3 millimeters in length, right? Again, if we just took the predictor from this observation, just the length of the animal, and plugged it into our model, right? The black line, the equation for this black line, we don't exactly get the the true length of the head that we observe in the animal that was 77 centimeters in body length, right? We get an estimate of that head. That estimate is 86.4. All right. So again, just subtracting the true value of y, right? Y of x minus the predicted value of y from the model, right? By plugging in only x into the equation of this black line, which is y hat of x, we get the residual. So subtracting that difference, right? We get 85.3, which again was the true length of the head of an animal of 77 centimeters in length, minus the predicted length of the animal based on this equation when the animal was 77 centimeters in length. All right. And that is negative 1.1 millimeters. All right. So again, a negative residual means that we have an over prediction by the model. And that's exactly what we're seeing here. I'll come back to that in just a second. A positive residual would mean that we have an under prediction by the model. Again, let's look at what we got here, right? The model's predicting 86.4 millimeters in head length for an animal that whose head we actually measure at 85.3 millimeters in head length, right? So that means that the model has made an over prediction. This X denotes exactly where that animal's um, total body length and head length is, right? At 77.0 and 85.3 XY coordinates in this Cartesian coordinate plane, okay? So that's where we're at with our true observation, right? And our model is this black line. So at that body length, right? At that predictor level, or that predictor value, right? The model would say that we should have a longer length of head than we actually did. All right. So again, that is a model over prediction. All right. The opposite can happen too. Like here, let's say that we have another animal that we're adding to this data set, right? That had a body length of whatever this is, 85, 86 centimeters in length, right? Whose head we actually also measure. And this animal had a pretty large head, right? Maybe 100 millimeters, 99 millimeters in length. So again, in this particular case, now looking at this plus sign as a data point for an actual animal, the model is under predicting the head length for that animal. Okay. Because if we went by what the line says the X value should be, we are way under, right, than the reality. And again, here in the triangle, we have another example of an over prediction by the model, right? Reality's here, right? For this animal of 97 centimeters in length, right? Like the head length was whatever this is, 94 millimeters, right? But if we went by the model, only putting in the length of the animal here, and then trusting this black line to tell us what the head length should be, right? We would be over predicting or saying that the animal or making an estimate of a longer head for an animal of that body length. Okay, so that's what we mean by residuals, basically a measure of error. Okay, so okay, what do we have here? So again, yeah, so calculating the residuals, right? We just went over that. Right, we have our model estimated parameters there. Observation 77.83. Okay, I'm basically going over how to what we're substituting exactly that I was just talking about in the slide before. Okay. And then the residual calculation there again. Negative 1.1. And again, all negative residual values means that the model does an over prediction. All positive residual values means that the model does an under prediction. All right. Residual plots. Oh, yeah. Residuals can be summarized into something called a residual plot. All right. So we'll begin to see this a lot in Lab 9, I think. And these residual plots, I'm trying to get my own face out of the writing. Otherwise, I can't read. Jesus. Let me see. There it is. Yeah. So these residual plots ultimately evaluate how well a linear model fits the data. All right. So again, this residual plot is how off the observation is to reality. Okay. And uh, you get this summary, okay, for the entire range of X, all right, for the entire range of your predictor variable, all right. You take all your observations and then you calculate the residuals, like how off they were model-wise compared to like true observations, all right. Uh, minimal a minimal Y range, meaning that all the residuals are pretty close to this 0 point, right? A zero residual means that there's no difference between a true observation and a predicted observation by the model. So you're never really gonna get anything on zero, right? Especially if it's a numerical continuous variable, right? You will be wrong at some level of at a certain decimal point. But again, the smaller the range of Y, the more accurate the model is, right? Because all of the observations are pretty close to the predictions. That's what that means. All right. If residual plots show random scattering, the model is a good fit. All right. You definitely wouldn't want all of the residuals to be positives before a given X, say 85, and then all of them to be negative above a given X, say 85. If everything, all the observations for residuals were here in the positive range, and all of them were negative after 85 here, that would be an issue. You want the scattering to be random in order for your model to be considered a good fit. All right. Another issue would be if residuals have patterns. All right. If the hyperbola emerges here, right, or a parabola emerges here, that would be a bad thing too. So that means that there's a confounding variable that we're not understanding that's structuring how much or structuring the directionality of the error that we're measuring. Okay, so again, residual plots evaluate how well a linear model fits the data. Okay. Right. So I think that what we have here is basically data and a line that represents the trend of the data or the linear model, and then the associated residual plot down here. All right, so it's a pretty good fitting model, actually, right? So we see the line, the data, and then we take the difference, right, between the y that's actually observed, right, like the y in that coordinate for that point that I'm hovering over, and then the y at that same x, right, that's predicted by the model right here. Okay, so there's a slight difference, right? Like the y predicted by the model is there for that same dot that I was just hovering over. The y observed there is right there. And that difference, right, would be the first residual here or the second residual here, actually. Okay. Yeah. So that, yeah, second residual. That would be a model under prediction. Yeah. So this is the error is positive. Anyway, so on and so forth. You do that for all of those dots and you get this residual plot that again looks pretty random, right? And that relatively nicely cluster around the 0 point. This dotted line would be no error at all. All right. Here, there's some issues, right? We're talking about patterns. Like you don't want to see patterns here. You want everything to be random. And for whatever reason, right, basically there's a trend right there. You see that trend? That means that the relationship is not truly flat linear, but maybe more of a polynomial relationship that it's not appropriately measured with a single line, right, with the slope intercept equation. So the residuals will give that away, right? All of the errors are under all of the model predictions are overshot in this range of the x-axis right here. All of them are undershot in this range, and then they become overshot again. So you get this trend. That would be a bad fit. And here, there's just very little predictive capacity, right? So the residuals are just huge. Like, yeah, they're very large across both positive and negative values, and they look random but still huge. So that's not ideal either. Okay. Okay, a couple more conceptual questions. All right, I'll let you guys do this. This is pretty straightforward stuff, the conceptual questions. I'll let you play with that on your own. The bottom line is that you want to look at the residuals always. All right, this will be one of the standard summaries that we'll print on R for every one of our linear modeling approaches. You want to look at them always as important considerations to gauge if you should use a linear model for the relationship in question at all. Okay, so that's the idea for the residuals. Anyway, final point here, strength of a correlation. So a correlation um, is more or less how tight the residuals are around the model. Okay. And it basically gives you the net strength of the linear relationship here. Okay. So correlation, which always takes values between -1 and -2, describes the strength of the linear relationship between the two variables. All right. We denote this correlation by R. All right. Formally, we can compute the correlation for observations. Those are all different observations, right? X, Y points on the coordinate plane using the following formula. All right, where x hat, y hat, s sub x, and s sub y are the sample means and standard deviation for each variable. All right, calculating this statistic is obviously complicated, and a lot of errors are going to be made. So we will always generate it computationally. All right, don't worry about this too much. So here we visualize something called the correlation coefficient, R. Okay. And the more linear um, data are, the closer R is equal to either 1 for a positively linear relationship or -1 for a perfectly negatively linear relationship. All right. And yeah, so again, perfect linearity would be obviously that for every 1 unit you go to the left, on X, right, you go 1 unit up on Y. Okay, so that's what that would be. And just falling perfectly on the same line, right? All of the observations. So yeah, an R of 1 will almost never happen, or -1 will almost never happen. But there are instances in nature, right, where you can get real world data and get some pretty nice, uh, very linear R's, right? Like again, the closer you are to 1, the more linear all of your observations are. So, all right, a couple conceptual questions here. Sure how I'm doing on time. I think this is enough. We can pick it up on Wednesday. Okay, so feel free to go over this conceptual questions for the correlation. It's a couple of problems right out of the book, but I'll let you guys do that on your own. At this point, I'll stop and take care, everybody. I'll see you on Wednesday. I'm not sure if I'll be there in person, but I will do an asynchronous video most likely on Wednesday. Okay, take care, everybody. Bye bye.